Section 7.2 is focusing on just reflections. So yesterday we got just a brief overview of all of the different types of transformations. Today we are going to focus on just reflections. And a reflection is a type of transformation that uses a line that acts like a mirror. That line is called our line of reflection, and we'll need to refer to that line frequently of where that line of reflection is when we're talking about things in a coordinate plane. If a point that is not on a line, and I want to emphasize that, not on a line, is reflected in the line, and the phrasing there, in the line. A lot of kids say, what does that mean, in the line? It just means like across the line. So I'm going to go ahead and write that down because the book always says in the line, and I think that terminology sounds weird to us.
Sometimes, yeah.
So if a point that is not on a line is reflected across a line, then the line is going to be the perpendicular bisector of the segment that joins the point and its image. Now, what we mean by that is if we go ahead and draw this reflection, so point P is reflected across this line. Think about it as if like you're taking a piece of paper and folding it in half right on that line.
Okay.
That point P prime would be somewhere right over here, right?
Okay.
Now, what this is saying that if I draw in a segment, get a different color, a segment that goes from that point, from the pre-image to the image, that the line of reflection will actually be a perpendicular bisector of that segment that I could draw in.
That makes sense because when you make that reflection, that image and pre-image have to be the same distance to that line of reflection.
Right.
And just because they're the same distance, like if you drew, let's say you drew a point like further down over like below, like same distance from M.
So like maybe if I said this was...
But if you connect that segment, that wouldn't form a perpendicular or wouldn't form a right angle there. And that would make sense because if you fold it, it's not going to land right on top of it.
Exactly.
All right. Reflections, I like what you said. When you fold it, it's in a sense, it's going to land right on top of it.
Exactly. Now, here's a new question. What if a point is on the line? Because this starts off with if a point not on a line is reflected. So what if the point is on the line? What if I give you point P right here? Let me call it a different point. Say point Q.
Okay. Then wouldn't the image be the same thing as the pre-image? So Q prime would be at that same location. It wouldn't really go anywhere.
It wouldn't go anywhere because if you think about it, if you're folding it, if it's on the line, it's still going to be on the line.
So it wouldn't move anywhere.
It wouldn't move anywhere.
So Q and Q prime are basically the same.
Yeah.
Same thing.
I should say is the same as. Exactly.
So the image and the pre-image would be the same.
Yes. All right.
Okay, so we're going to do some reflections in just a minute, but we do have a theorem that goes along with it. Now, the notice theorem, nice and short, it says a reflection is an isometry. Now, we learned about this word actually in class today, all right? And that word isometry, can you recap what that means again?
If it's an isometry, then all the parts of one would be the same as all of the parts of the other.
And so, like, what do you mean the one?
The pre-image and the image.
Okay, so
pre-image is really congruent to your image.
Good.
Now, we talked about, like, all of the angles, all of the segments, all of the distance between any 2 points is going to be the same.
Okay, and I like that you said any of their parts. So you end up where your pre-image and image are going to be congruent to each other in a sense, right? Nothing really is changing, just where they're located in a sense. Right?
Right.
So here's an example, and we're just doing a little sketch. We're going to actually do some reflections, perform some specific reflections in just a minute. But if we were doing a sketch, let's say this is this green line here. This is the line of reflection, okay?
Okay.
And we're wanting to reflect segment AB in that line or across that line, all right? Now, what would be, like, and I'm just going to do a sketch. We're not going to actually do this for real. We could.
Yeah.
If I was just sketching this, how would I maybe what would be a good process of doing this?
Well, I'm thinking I've got 2 points, and I just talked about on the last slide how to reflect just a point.
Yeah.
So could I just do each point individually and then draw the segment that connects them?
I think that's a great idea.
All right. So I know that, like, if I go ahead and try to draw a segment that would be perpendicular to our line,
So like something like this would be kind of...
As long as it's a perpendicular bisector, yeah. So I can say, okay, that's bisecting and it's perpendicular. Then that would be my point A prime. And I could do the same thing down there for B. So if I start to draw in a little dotted line and say, okay, then I know that if that dotted line is perpendicular and bisecting that segment, then that's where my B prime would be. And then I could go ahead and draw in the actual segment of the reflection to connect A prime and B prime.
Now, this is a sketch.
Right. It's not going to be perfect.
Yeah. Now, one thing, and they should notice they should land on that point right here on the line isn't going anywhere because it's staying on the line of reflection.
Right.
Now, do you need to draw in the dotted lines and show perpendicular and bisecting? Not necessarily, because all it says is, if it says just sketch the line of reflection, but this is a good way to kind of get a visual of kind of why it's working.
And I'll tell you guys that, if we would have a test question or a quiz question maybe that was like this, that said we want you to do a sketch, if we don't think it looks like it, then we're probably not going to give you credit for it. But if you've shown us the dotted line to say that, look, this is why I think it's here, then we're going to be more likely to maybe give you some points for that. So it's really not a bad idea to put that on.
It kind of it's kind of like when we asked you to, back in chapter 6, draw an equilateral pentagon, and if it didn't really look equilateral, but you had all the tick marks there to show it, then that
gave
works.
it to you,
a sketch, remember, we're not going to be perfect at it, right? So just adding those things in wouldn't be a bad idea.
But I love how you made them dotted to make sure we realize that's not the line we're
Yeah,
reflecting.
the line we're talking about. So basically, in the end, if I was talking about this theorem, right, basically segment AB, which is your pre-image,
should be
ends up being congruent to, how would I write this?
A prime, B prime.
Yeah. Don't put AB prime, because then you're saying A, I didn't mean to, I did a little tick mark right there. You're saying then A, B prime. That's this segment right here. So how you name it does matter. So AB prime, that segment is congruent to the original pre-image.
Yeah, A prime, B prime. All right.
Okay? So,
all right, we are going to perform some reflections. And notice that we've got a beautiful coordinate plane because it is so much easier to do reflections and really to do a lot of these different transformations when we've got a coordinate plane. So we're going to see that a lot this chapter. All right, first one says we're going to go ahead and we're going to reflect all of these points, W, M, and Z, in the y-axis. So let's just identify, first of all, where our line of reflection is.
okay.
Okay, so where is the y-axis?
The y-axis is the vertical axis.
Absolutely. No. Oh, yeah, y-axis. Sorry, I was thinking it said x, even though I clearly said y. All right, there's my line of reflection. Now, we want to go ahead and label the points that we've got to start with. And notice in our book, what do they always start with for our pre-image? What color?
I think we went with blue.
Yeah, the book's always blue for pre-image, so we're going to go ahead and start with blue. So, or I am at least. And if you guys want to do that on your papers, you're welcome to get out some colored pens and do the same thing. Point W is going to be at the point -3, 3. So I'm going to go ahead and label that as point W. And M will be at 2, 4. And Z is going to be at 0, -5. And we're going to then come up with the image of these points. All right, now when we reflect across a vertical line, we know that we want our line of reflection to be perpendicular to our actual transformation that's taking place. So what do you know is going to be nice about that if I've got a vertical line? What's perpendicular?
Well, then a horizontal would be perpendicular.
So we really just need horizontal movement to happen here. Okay? So what I'm going to do to start with W, how many spaces, if I start to count, because on a coordinate plane we can count spaces, how many spaces from that horizontal line of from the vertical line of reflection is that point?
So I got to count, so that'd be 3 spaces.
3 spaces. So I need to continue where?
3 spaces to the right.
3 spaces to the right. So this should be my point W prime.
Okay.
Now, do we need to draw in the little boxes to count or anything?
No.
We won't need this little line. I just wanted you guys to realize where that's coming from. All right, let's talk about M prime. So how many spaces from that line is M?
I counted 1, 2.
So then we need to continue,
1, 2.
and there's going to be our M prime.
Now, should we give the coordinates of it? Should we write
Yeah,
the
we
coordinates
will.
down?
We will. And then what about point Z?
Well, it's on the line of reflection, so Z prime stays there.
Exactly. Same point. All right, now, I love what you said. So let's go ahead and let's label our coordinates for each of these. So we've got W. Let's talk about what is W prime. What is the ordered pair for W prime?
It's 3, 3.
3 comma 3. What about the ordered pair for M prime?
M prime is negative 2, 4.
Love it. And what about Z prime?
Is the same, so 0, negative 5.
All right. I want you to look at these ordered pairs. Do you see anything? Do you notice anything looking at just the original, the pre-image compared to the image, those ordered
Okay.
pairs?
So I'm looking at the, like, choice A. I look at the image and I look at the pre-image, or the pre-image and then the image. And I notice, well, the Y coordinates were the same. They're both 3.
Absolutely.
The X coordinates, like in the pre-image was negative 3. The X in the image becomes positive 3. So it was kind of like opposite.
Okay.
Okay, so I'm looking at B as well. So the Y's were the same, and yeah, the X's were opposites. Now in C, everything stayed the same, but
So the
we
Y's
knew
were
that-
the same.
Yeah,
But what's the opposite of 0?
just there's no opposite. 0 is just 0.
Yeah.
Okay.
So in general, if I have an ordered pair X comma Y and it's reflected in the Y axis, then what can you say about its image? What do you notice was happening every time?
well, the X's were opposite, and the Y stayed the same.
So it'd be the opposite of X comma
Mm-hmm.
Y. Now, that's a neat pattern and a neat thing that we're going to notice. Do we have to memorize that pattern?
No.
No. But it's just kind of a neat pattern of something that we're going to notice will happen every single time if we're reflecting in the Y-axis or across the Y-axis.
And I want to hit on Ms. Huggerby mentioned something because the line of reflection it was vertical. She made the comment that our reflection kind of went horizontally, right? So that also supports why the Y coordinates did not move,
Right.
The Y coordinates stay the same because all you're doing is going left or right. So if you're reflecting across a vertical line, okay, and we'll see some other ones, think about what's going to stay the same is you're not going to be moving up or down any, you're just going to be moving left or right.
Right.
So we kind of remember that, okay? Now, let's try a different line of reflection. Notice this time around we're going to do a reflection across the
X-axis.
X-axis. So I always like to kind of highlight that, all right, just like Ms. Hochgraby did as well. And we're going to reflect individual points. Now, if you don't have, Ms. Hochgraby mentioned about doing blue and red. If you don't have color,
That's okay.
does it matter?
No.
No, because
How we're labeling it is.
how can we tell, like if I go back real quick, how do I know by looking at this graph which ones are the pre-image versus the image?
Because the pre-image will always just be the letters, where the image is always the letter prime.
Perfect. Just wanted to remind you of that. Okay,
Yes.
so let's start. Notice they're doing the same point. So let's do negative 3, 3, your W. So if I reflected that in or across the x-axis, right, this time, notice I'm dealing with a horizontal line.
Okay.
All right? So what kind of lines are perpendicular to horizontal lines?
Vertical lines.
Vertical.
So I want vertical movement.
So I'm only going to be going up or down in a sense.
Okay.
So I'm going to kind of do what Ms. Hochgraby did is count to that line. So if you think about it, there's 1, 2, 3.
Okay.
Okay. So then I'm going to keep going. 1, 2, 3. Okay.
So that would be my point, W
Yeah.
prime.
And again, you don't have to draw in, and Ms. Hochgraby only did it once. Most of the time you don't. Okay?
Right.
And I actually never do.
Yeah.
Right? It's more just the counting, and it's hard for us to show it without kind of doing that. So W prime is that one. So let's go ahead and write down what's the coordinates for W prime
So
is.
W prime would be at negative 3 comma negative 3.
Okay. Now let's go ahead and do M.
So that was at 2 comma 4. So I noticed that I'm going to have to count down 4 spaces to get to that line. So I'm going to continue 4 more spaces down, and I should be at 2 comma negative 4.
Now, okay, I'm going to challenge you guys to think about on this next one, based on the fact that, remember the last one when we reflected across the y-axis, there's kind of a pattern. There's something we notice happened when we reflect across that axis. Look at your pre-image and image and kind of think about, do you notice a pattern happening, all right, before we actually reflect it? So do you see anything?
I do.
Okay, so I want you guys to think about it. So if you want to pause for a second, think about it. All right. What are you noticing?
Well, I noticed that the X values are exactly the same in the pre-image and the image, and the Y values are the opposites.
So if we kind of made a prediction, what do you think Z prime is going to be?
I think Z prime is going to be at the point 0 comma 5.
All right, let's test it. So if we know that Z is 0, negative 5, and I reflect it across the x-axis,
I know that I'm cutting out 5 spaces.
and then going up 5 again.
That's where our Z prime will
Hey,
be.
you got it. Nice work. So what are we noticing? Well, when we reflect across the x-axis, you said the x stayed the same, so that would be just x, and the y is opposite, so that means it'd be a negative y, which is saying the opposite of y.
Great.
Good.
Okay. Now we're going to get a little trickier because, horizontal and vertical movements are pretty easy to do. The hard part comes in when we start talking about moving across a line that has any kind of a slant to it at all. So first of all, we're going to be reflecting in the line or across the line of y equals x, which for some of my students, that's kind of a thing to try to remember from Algebra 1.
That's a challenge just in itself. Yes.
And this is at least students in the past. Now this group may just be phenomenal. They may
Yes.
say,
You
I know
remember-
exactly what that looks
You
like.
remember everything from last year, right?
Yes. And just as a reminder for you guys, you could think about that as slope-intercept form if you wanted to. And you
Okay.
could say that that's like y equals 1x plus 0 if that helps to think about a slope and a y-intercept, where your slope is 1, your y-intercept is 0. You could think about this that every x value and y value should be the same.
So if x is 1,
If
y
x is 1, y is 1. However you want to think about that is totally up to you. To graph that line, because we always want to have that line of reflection on there. So we could go either way. Y-intercept is 0, and I'm going up 1 over 1 every time. Or notice that when I do that, my x and y values are the same every time. 2 and 2, 3 and 3, 4 and 4, etc.
So the key is you have to know that line of reflection first.
Yes. So I'm going to go ahead and draw in the line of reflection. That's what I'm going to reflect across now. This is going to be a little trickier.
Okay.
Now, I'm going to go ahead and plot all of the points A, B, and C on the graph, and then we can look at each one individually and kind of how we're going to reflect that. So A is at 1, 0. B is at -2, 1. And C is at 3, -2.
Now I do something a little different. I do 1 point at a time. So if you want to just plot 1 point at a time, you can do that.
Okay.
Now that's C, right? Not C prime yet.
Oh, sorry, C.
That's
yeah.
okay.
Yes. All right, now we are going to take a look at each point individually.
Okay.
All right, so let's start with just point A. We know that we want the pre-image and the image to form a line that would be perpendicular.
Okay.
So I want to think for a minute, what do we know about perpendicular lines?
They form a right angle.
Form a right angle.
Okay. If we're talking about coordinate plane, is that
Uh-huh.
what you're thinking?
That's what I'm
Laura?
thinking.
Okay. Their slopes are opposite reciprocals.
Okay, so what was the slope of this line that we had here?
It was
The original, the line of reflection.
The original was 1.
1.
So then for the perpendicular slope would have to be -1.
Right. So I'm going to think just for a minute about if, and usually I would count down and to the right to say down 1 over 1, down 1 over 1.
Yeah.
But since I know I'm having to go across my line backwards, I'm going to go up 1 and back 1.
Okay.
All right. Now, notice that if I go up 1, I'm already to the line.
Yes.
And if I go back 1, I'm already across the line. That right there, this line that this is on, if I kind of continue this line is perpendicular to my original line.
Which is one of the criteria when you're doing a reflection.
One of the criteria. And what do you notice about this point that we actually have already put on there just when we were counting slope?
What do you mean?
Like,
I'm not sure what you're asking.
Just compared to my original point. Like if I look at that original point, it's about half. This is a diagonal, really, of
Yes.
that box,
Yeah.
right?
Yeah.
So it's like half of a diagonal to
Oh,
get
okay.
to the line.
It's the same distance
It's
to that
the
line
same
of reflection.
distance.
Uh-huh.
So this point right here is going to actually be my point A prime.
Okay. That makes
All right?
sense.
So we can think about slopes because slopes really help us to get that idea of perpendicular. If it helps, guys, you could even just draw in a line and then just look to you're going to notice that you're going to be counting really parts of diagonals if
Yeah.
that kind of helps to think
Yeah.
about that. To be able to find where that new image will be. So what is that ordered pair for
So
A
A prime is 0, 1. Another thing you could do, and we kind of mentioned this earlier, is about the folding idea
Yes.
too. You could kind of see where does it match up. Okay,
Right.
because it is a perpendicular bisector. We learned how about perpendicular bisectors back, way back in early chapters, first semester.
Yes. All right, let's take a look at B.
Okay.
All right, point B, I see it right up here. I'm going to go ahead and draw in kind of just a perpendicular line again. So using that idea of a -1 over 1 slope. So if I count down 1 over 1, down 1 over 1, down 1 over 1, and I could continue that, right? And I could draw in that line to see, okay, I know that it's going to be somewhere on that line.
Yes.
Now, as I'm counting for this one, I really need to really think about, again, the diagonal idea because it's not even spaces.
No.
But I noticed that to get from B to the line, it's really one whole diagonal and then a half of a diagonal.
Okay.
So I need to count, here's my half diagonal and one whole diagonal, and where that falls should be my point B prime. Is that?
So that is 1, -2.
Yes. I'm going to go ahead and get rid of these extra pieces just that way we
Good.
can see it. And there's my B prime. So 1, -2. Now, I know this is a little trickier, but guys, try the
1,
next one.
-2.
Sorry. Thank you.
You're talking and
I am.
writing at the same time. I'm guilty of doing that all the time.
I want you guys to try point C on your own. See if you can do it. Okay, so what would you do for point C?
I would do that slope idea. So actually, you know what? I could also do. There could be a pattern, right?
There could be a pattern.
Let me see. Let me just test it before
Okay.
and we can then do it. If I'm looking at point A first, and I notice the pre-image and the image, it looks like, just the X and Y kind of switch places.
It does look
Okay,
like
let
that.
me look at B. And it does the same thing. So if I am going to take a stab at this, I'm thinking C prime is going to be -2, 3.
Okay.
So if I plot that on the coordinate plane, let's just put it there, -2, 3. And I kind of do that, connecting those like doing the line like Miss Hochgraby's doing. Does that have a slope of -1? Yes.
Yes.
And that distance kind of idea, it looks like there's 2 whole diagonals, a half, so a half and then 2. So it works out.
It does. So that kind of helped us to get to our pattern. So do we notice? If the X comma Y is reflected in the line Y = X, then its image would be what?
YX.
Y
Just-
comma X.
Yeah,
Just
switch it.
flip-flops those X and the Y values. Perfect.
All right, now, Ms. Hochgraby gave us a good start on this one. We're going to do a very similar line, okay? Notice, though, the line reflection this time is Y = -X. So what's changing about this line compared to the one we
All
just
right.
did?
So I'm thinking it's the slope that's changing. The slope's now -1.
So the slope is -1, but the y-intercept is still
Still
0.
zero.
So let me graph that line. All right, so we're starting at 0 and then going maybe down 1 to the right 1, down 1 to the right 1, or you could go up 1 to the left 1, just kind of up to you. All right, I'm not great at drawing lines always, so that's why I'd use
Use the beautiful
the
line tool.
tool,
I know. I love that line tool.
Okay, so we are plotting, let's plot 1, 0 first. That's your A.
Okay. So and we're going to go ahead and reflect it.
What do you want to do?
Well, I'm thinking because those have a slope of the line of reflection is a slope of -1. To be perpendicular, I need a slope of +1.
Okay, so that
for this
means I
line.
would go up 1 to the right 1, but that goes away from the line. We want
Yeah.
to go across it. So maybe down 1 to the left 1.
Yeah, because that's 2 negative moves. That'd make it positive too.
And even kind of using more of what Ms. Hochgraby said instead of spending all this time. Notice how also the distance from that line, it's kind of half a distance in a sense of that diagonal. So that's probably as far as you need to go. If you need to draw that line in or draw in more points to kind of get a visual, but this is your
A prime.
A
Okay.
prime, which is the coordinates are
0, -1.
all right. Now, I'm going to encourage you when we do this next one, after we do it, think about if you're noticing a pattern yet. all
Okay.
right? So -2, 1, there's your B. If I reflect that across that line Y = -X,
Well, that's still
right.
just a half a diagonal away.
so
Those little half diagonals are kind
up
of
1
nice.
to the right 1.
Yep, that'd be my slope of +1
So B prime would be,
at -1, 2.
okay, so hopefully you're noticing something, or if you're not, you can always do this. And guys, the patterns are not something you have to know or memorize. However, you might be asked to explain what you notice after you do it. So you still can do the reflection and then explain it later.
Right.
If you can remember the patterns, then you don't have to actually always perform the actual reflection. All right, so what are you thinking?
Well, I'm noticing that all of those points, they still are flip-flopping the X and the Y, But like on the first one, I noticed that the y value was the opposite of its original x. The second one, they're both opposites. But when I looked at my 0, the opposite of 0 is still 0. So I'm wondering if it's maybe just the opposite of y, comma, the opposite of x.
Okay. And kind of what she's saying here, if you look at, because A has that 0, so you can't really, there's no opposite of 0. But if
just
you look
0.
at the B point, -2 and 2 are opposites, 1 and -1 are opposites, and they flip-flop spots.
Right.
So what would my C prime
So
be?
I'm thinking maybe it's going to be 2, comma, -3.
So you have to do the flip, kind of switch spots, and do the opposites of each coordinate,
Right.
Or ordered pair. So that makes if I reflect it on this line, across this line, the image ends up being
The opposite of y, comma, the opposite of x. Now let's check that with our point C.
okay.
Make sure.
So C is 3, -2.
Hey, look, that's just a half
I know,
diagonal away
we
too.
gave you easy points. So
We did.
down one to the right one would be a slope of 1. So C prime is 2, -3.
Perfect.
So we had the right idea. Good job.
All right. And this is just a way to recap it. If you guys want to recap, what did we say about when we reflected in the x-axis?
Okay, so
what happened?
x-axis is your horizontal axis.
Right.
So all I'm doing is moving vertically, up or down.
Uh-huh.
So the only thing that changed is your x, or your y, sorry. So the x stayed the same, and then the y was opposite.
Exactly. And guys, I want you to notice how we're writing this, that the point x comma y is mapped to x comma -y.
Good
And
comment there.
we want to make sure that that's the format we're using when we're describing these transformations.
Okay,
Okay, so what happened with I reflected across the y-axis?
so that's your vertical axis. So you're moving horizontally left or right only. So that means your x is opposite and your y stays the same.
Perfect. And what about when I reflected across the line y equals x?
Okay, so that was your diagonal line
With a positive
with
slope.
a positive slope. So all it happened was switching the y and the x, or the x and y, so it became yx.
Perfect. And then the last one that we just did, we noticed when we had a negative slope.
So then it flipped and make opposite. So -y, -x.
Okay. And that may just be a good little spot to have just one little nice convenient place to look at those later.
Now you won't have these you can use on a test or anything like that. So
Right.
it's not really, guys, about memorizing these.
No.
Like if you remember them, great. If not, no big deal.
You can always
Okay?
perform it.
Exactly.
All right.
Now, let's do some other reflections, but these are a little bit different because notice the line we're reflecting is not a y-axis, x-axis. So let's make sure we know what the line is, and then all we're doing is reflecting 1 point. That's
Okay.
all we're doing, okay?
Piece of cake.
So tell me about this line x equals 1.
All right. Well, I'm thinking back to algebra, and I remember we talked about like Hoy and Bucks. And most of you guys probably have seen those before. If you haven't, just a quick recap. Horizontal lines have a slope of 0, and the equation is y equals some number. Vertical lines have the undefined slope, and the equation is x equals some number. Because this equation is x equals some number, I know it's a vertical line, and it goes through the x value of 1. So
Okay.
if I go through the x value of 1 and draw a vertical line, that's the line of reflection.
Awesome. Okay, now that's not the same thing as the y-axis, but it still hints this idea, a vertical line. So think about if we're reflecting the point 5,3. Let me put the point 5,3 on here. Point R. If I was reflecting point R across that line that's a vertical line,
Right.
okay, all I'm going to be moving that point is
Just vertically. Or just horizontally.
horizontally.
Sorry.
So I'm moving either
Yes.
left or right.
Right.
So if you think about it, if you're only moving left or right,
We're just counting.
Yeah, and you're just counting. And what's going to stay the same though? If
I
you're
know
not-
that the y value is not changing.
So
here.
keep that in mind. That's just something to kind of keep in mind. So
Okay.
I'm going to count because vertical and horizontal are perpendicular. So I'm going to count to the left 1, 2, 3, 4, and keep going. 1, 2, 3, 4. So there's your R prime. So what is my coordinates?
Coordinates would be -3, 3. So yeah, look, that y value did stay the same.
Now the x values we're not
not
just
just
opposites. Okay, but think about it. 5, the x value 5 is 4 away from the 1, which is where the x coordinate on that vertical line, and -3 is also 4 away. The distance from here to here is 4. The distance from here to is 4 because it has to be
Right.
That perpendicular bisector idea. Now, one more thing before I move on, I was just thinking about this on the last time we did. when you're when it says give the image, make sure that you give the name of it and also give us the ordered pair. All right. So get in the habit of doing both of those things.
Right. Okay, we've got another one. Here our line is y equals -3. So what kind of line is this going to be?
Well, that's horizontal because it's a y equals a number, some number. So y equals -3 is going to look like that.
It's going to go through the y value of -3. And then they give us point K is at -4, comma 2. So there's K. And how am I going to be moving here to be perfect?
All you're moving is vertically. So you're just going to count down because that's where the line is at.
So since I'm 5 spaces from the line, I need to go down
5 more spaces.
And there's going to be our K prime. All right, so what is the ordered pair for K prime?
It's going to be -4, -8.
Great. And again, that's how we'll be naming them.
Again, notice what stayed the same was your x coordinate this time because all you moved was vertically. All right, one more definition, and this is something you've learned about, and we've kind of already mentioned a little bit of this. This term, line of symmetry. This is a line that a figure in a plane has if a figure can be mapped onto itself by a reflection in that line. All right, so what does that essentially mean? Okay.
So that means that basically I could fold a figure in half and it'd be right on top of itself.
Exactly. Now, it says if a figure. So do all figures have line of symmetry?
No, not at all.
No, and it says the number of line of symmetries really depends on its shape.
Okay.
All right. So we're going to try some examples on the next slide to kind of see what that means.
Okay.
Okay. So for example, an isosceles triangle.
All right. So if I want to be able to fold it onto itself, I couldn't draw a line that would be like horizontal or anything because it would definitely, I'd have a point over a flat surface.
And yeah, if you like what she's talking about here, if you fold it, it's not going to map to itself.
So I'm thinking we're going to need to draw a line that goes from that top point, and basically it's just the height. So if I draw a line that goes through that base, and it should bisect the base, it should be a perpendicular bisector, I know that I could fold those two on top of each other.
And the reason why, here's the key, because it's an isosceles triangle, right? If I know that those sides are congruent, so if I fold it, those sides are going to match up. Even these angles down
base
here
angles
are
would have been
congruent
congruent.
as well. So those are going to fold on top of each other. Now, can you think of any other line of symmetry? So if I draw from this vertex, if I draw that in, is that going to work?
Not if it's just isosceles. I bet on the next one though, the equilateral, that would be true.
And the reason why is because this side right here, this side and this side are not congruent. So they're not going to map onto each other. Again, that key here. So determine the number, there's just only one. But equiangular means equilateral, right?
Right.
So all the sides are congruent, all the angles are congruent. So how many lines of symmetry do you think there's going to be?
I think there's going to be 3. I think there's going to be one kind of that looks just like the one we just drew. But then there's going to be one going from each vertice through that opposite side.
Sometimes they'll say just determine. Sometimes they'll ask you to draw all of them, just to kind of keep in mind.
Okay.
All right?
So a square, I'm looking at that one. And guys, you can try some of these on your own too.
Uh-huh.
A square, I can see that I'm going to have a vertical line that would cut that in half.
Whoops. Paused on me.
There we go. Vertical line. And I'm also going to have a horizontal line that will cut that in half. But then could I also go through each of the diagonals?
Okay, that's a good thought. Let me just draw one and sketch it. And this will work because with the square, the opposite angles are congruent, but also each pair of opposite angles are bisected.
Right.
Okay, because it's a rhombus idea. So these angles are congruent to each other, and all of these sides are congruent. So everything is going to be basically mapped to itself. So
Okay.
we could probably do that with the other diagonal.
Okay, great.
So a square has
4 lines of symmetry.
And what's kind of unique about B and C, the two that we just did,
They're
is
both
they're both
regular.
regular. So regular, notice how many they have is based on how many sides there are. Okay, so a regular pentagon would have 3 lines of symmetries as well. 5. I'm saying, I'm
both
thinking
ready
5.
yeah.
Yes.
Okay, rectangle. Here I could see a vertical and a horizontal line, but I could not do any diagonal ideas because they're not going to be mapped onto itself.
So look, if I do that, if I fold it, and just think about like your piece of paper in front of you. If you try to fold it diagonally, it's
just
not going to map
no.
onto itself. So these are the only 2 that work. So when it's a regular figure, you have a lot more. Would a scaling triangle have any lines of symmetry?
No,
No,
it
because
shouldn't.
there's no congruent pieces that are going to map to itself.